Okay, let's get started. So we're nearing the end of our conservation and dissipation of energy topic. So we only have 3 more usual lessons to go, but I'm going to try to do a 2-in-1 today to just get it done. That way we can finish this topic before the half-term break. So I have linked, let me just link it again. It should be like a multiple choice thing, Louis, on Show My Homework, like a multiple choice quiz that's on Show My Homework itself. It's not like an attachment thing. Hold on, let me just quickly link it then. I think I can link directly to an assignment. Let me just find it. Calendar. Oh wait, no, sorry. Yes, here we go. Got it. There's the link there. Okay, so let's get started then. We have just a few notes that we need to get through first. Let me just quickly give that link over. Should be at the... If you scroll down, there's booklets there, a PDF version and a DocX version. I recommend opening up the Word document version so that way you can type things in as we go along. But we're nearing the few end pages of the booklet. The majority of the booklet are calculations that we have done and practiced before. If you're just joining, remember all of the previous videos on this topic are going to be on the YouTube channel and previous videos. There's also, I've organized it into a playlist so you can see which ones are part of this topic. So previously we talked about something called the law of conservation of energy. We did some calculations on it, but remember the theory behind the law of conservation of energy. What it says, and this is important for you to know, is that energy cannot be created or destroyed, only transferred. So basically what that means is if we're starting off in a system with 100 joules of energy, it's got to end up at the end being 100 joules of energy. It might have changed forms, so it might look like it's been destroyed or lost, but it hasn't. It's just changed into something else. Remember one of the examples we had is like the relationship between gravitational potential and kinetic. So for example, say you're at the say you're on a roller coaster and you're at the top of a roller coaster. By here, at this point, you have all of this gravitational potential energy because of your height from the ground. But then when you're going down this roller coaster, you're losing gravitational potential energy because you're losing height. Well, that gravitational potential energy hasn't disappeared. That energy hasn't just gone into nothing. It's changed form. It's changed form into things like kinetic energy or heat energy between the roller coaster and the tracks, or sound energy, things like that. But you have to understand that that energy, even though it might look like it have gone, even though it might look like it has gone, It's only gone from that particular store. It's just transferred into something else. But energy in general can't be created or destroyed. So we're going to link that in today's topic, which is all to do with energy, something called dissipation. Basically, okay, energy is obviously a very, very useful concept for us. We make use of it all the time in engineering. Basically, when we make tools in daily life, we always need to think about what is going to be useful to us as humans and what's not very useful. So when we're designing appliances or when we're using appliances, we always have to think about this concept of what is going to be useful energy and what is wasted energy. And these concepts, basically, you can just define them by the name. So useful energy, if you were just to even have a guess as to what useful energy is basically energy that is useful. Or I'm going to say energy that we quote unquote want to have. So a type of energy stored that we want to have. And wasted energy is energy that we don't want. So here's an example. Let's say we had a television. Here's my television. Think about all of the different types of energy that we've talked about, energy stores, energy transfers. In the chat, can you write one type? There are two types that I can think of, but one type of energy that we want coming from our television when we switch it on. What's one that we want? Spot on, Lauren, Tom, well done. We want light and sound. Now let's think about anything that, when we switch on the television, a type of energy that it transfers that we don't want, but it has anyway. What's one thing that we don't want from a television that's not particularly useful? Heat. Spot on. So like when you turn on the TV, if you touch the back particularly, you might feel a little bit of heat. Well, that energy is not useful to us in any way. I mean, like, remember, it depends on the appliance though. Like, because obviously if we're talking about a heater, then heat would be something that we do want. So when we're deciding on what is useful and what is wasted, it depends entirely only on that specific example of what device you're using. So a lot of it is just using logic, of using your knowledge of all the different energy stores and thinking about, okay, when I switch this on, what do I want from it? What am I looking to get? What type of energy am I looking to get? But what other types of energy do I get that isn't actually going to be useful to me? Another example is, let's try another one. Let's say we have a kettle. What is useful and what is wasted? So let's start with useful. What type of energy do we want from a kettle? Yes, spot on. With a kettle, we want heat energy. Notice how it's flipped around this time. So I don't want anyone here to think heat is always going to be wasted energy. Sometimes heat can be useful energy. Now, imagine it, you're switching on the kettle, you have heat energy going, that's what you want, but what other energy forms do you spot? Can you spot where it's not going to be useful to you? Oops. Yeah, very good. So when you turn the kettle on, it makes a lot of noise, it makes a lot of sound. Well, that sound isn't actually helping with heating up the water to make your cup of tea. So in that case, it's wasted energy. So remember, it's a lot of it is dependent on that specific example. Now we're going to lead into this concept known as dissipated energy, which is wasted energy. It's similar, but specifically it's wasted energy that goes into the environment. So dissipate, when we talk about what dissipated means, is energy that, and I'm going to put in quotes, is lost to environment. The reason why I have that in sort of quotation marks is because remember the law of conservation of energy. I don't want you to think that that energy is just disappeared or gone. It just means that from that specific appliance, it's just gone into the environment now. It's sort of lost from that specific system. It's lost from that appliance. Usually, the way that energy can sometimes be lost is typically through heat and sound. Typically. That doesn't mean that heat and sound are always wasted, but the way that energy becomes lost to the environment is usually through heat and sound, such as in this roller coaster example. If no energy was lost, if all of it was still kinetic or gravitational, theoretically, a roller coaster could have the same exact heights. Each sort of peak of a roller coaster could be the same exact height. But I want you to notice a roller coaster without an engine, the first peak is always the highest because that's the maximum amount of energy that that roller coaster can store in its gravitational form. You'll never see a roller coaster like this where if without an engine it can climb up to its highest peak because when it gets down here there's heat from friction between the roller coaster wheels and the track. There's also sound as it's going down. So some energy gets lost, which is why each peak has to be lower and lower. Same thing as if you have like a tennis ball that you're bouncing. When you drop a tennis ball, it bounces up. And then it bounces and it bounces and eventually it just stops bouncing and it's on the ground. The reason why that happens is because with each bounce, that tennis ball loses a little bit of its energy as heat when it hits the ground and as sound when it hits the ground. So each time it comes back up, it's lost a little bit of energy. And that energy is what's known as dissipated energy because that energy wasn't destroyed, it just went into the environment. It got lost into the environment, which is why when you drop a tennis ball, it's not going to bounce and come back up at the exact same spot every single time because there's always going to be some dissipated energy. So, when it comes to like engineering then, when we're building appliances or anything like that to make things useful for us, we want to make sure that we reduce as much unwanted energy transfers as possible. So we want to reduce the amount of wasted energy that we have. And the reason why we want that is because then we don't have to use as much resources, right? If we had like a TV that wasn't very efficient, it's going to be using more electricity to produce the same quality as a better TV that doesn't waste as much energy. Or like with a car, with some cars, their efficiency is really bad where you need a lot of petrol and it doesn't really go very far. So things like that we have to keep in mind so that way we don't have to waste as many resources if we make things a bit more efficient and by reducing unwanted energy transfers. So there's two main ways to reduce it. this is specifically reducing energy lost as heat. So if you rub your hands together, you guys know that friction creates heat, right? If you rub your hands together really quickly, you feel a little bit of heat in your hands. That is the heat from friction. So if we have a lot of friction, we're going to end up losing a lot of our energy to heat. So example, friction leads to heat loss, heat. So a lot of energy can be lost due to friction. So when we are wanting to reduce friction, we can use something known as lubrication, which is basically like any sort of substance, kind of like oil, that makes the friction a lot less. So the contact between the two objects, it slides a lot more easily. So that way there's less friction, so less energy lost due to heat. So lubrication reduces friction by giving smoother contact surface. Now the next thing is insulation. I have this picture here of this house using it like with an infrared camera to just sort of show that, like, if you look at the roof, like the loft here and the windows, there's a lot of energy loss coming from there. There's a lot of heat energy coming from there. So this house is losing heat energy as it's dissipating as heat. So then that's why we have insulation. So heat loss from houses. And insulation prevents heat from dissipating into environment. So basically it just tries to trap as much heat as possible. So that way then you don't have to spend as much money on your heating bills to make sure that your house is nice and warm, because the insulation's there preventing heat from dissipating into the environment. Okay. So all of this leads into this concept known as efficiency. Now we use the word efficiency in daily life quite a bit. Like for example, some of your teachers might have said to you, "Oh wow, you're a really efficient worker." One common misconception about what the word efficiency means in general, not just in physics, but in general, is people think being efficient means that you're fast. Like if your teacher says you're an efficient worker, that means you're a fast worker. But that's not what efficiency means at all. That's not what your teacher's saying. Efficiency in general, not just in physics, but the word means a lot. I can sum it up as a lot for a little. So for example, work produced in short time. So for example, if you were an efficient worker, you'd be able to get a lot done in a short amount of time because you're not, going on your phone, you're not getting distracted or anything like that. That means you're efficient. So now let's think about it in terms of energy. When we talk about something that's efficient, we're talking about a lot for little. This concept of a lot for little, meaning it produces a lot of useful energy for its input. So max amount of useful energy for its input. So for example, let's say we had a light bulb. Actually, let's say we had two light bulbs. They're both the exact same brightness. Actually, not the exact same brightness. Let's say that with both of these light bulbs, we're putting in 100 joules of electrical energy. So 100 joules of electrical energy is going into these light bulbs. For light bulb number 1, 80 joules is turning into light, is being transferred into light, and light bulbs heat up a bit, so let's say 20 joules is heat. With this light bulb, let's say it's 50 joules as light, and remember law of conservation of energy, that means it also has to be 50 joules as heat. Light bulb number 1 on the left hand side would be more efficient because the same amount of energy is going into each one, but light bulb number 1 is using the maximum amount in a more useful way. So it's better at taking what it's given and making something useful from it. Whereas it only has like 20 joules of wasted energy because we don't really care about having heat from a light bulb. Conversely, the light bulb on the right-hand side, it's less efficient. It's not very good at transferring energy from its input into being useful because it's wasting 50 joules. So when you think about what efficiency means, it doesn't necessarily mean that it is, oh, here we go. This is a perfect example to highlight this. Let's say that we had two light bulbs again. Let's say there's 100 joules going into this one, 200 joules in this one. Electrical energy. Same thing, 80 joules as light, 20 joules as heat, 100 joules as light, 100 joules as heat. So here's a common mistake. Some students might think, okay, let's look at how much of our useful energy is produced. Light bulb number 2 makes 100 joules. Light bulb number 1 only makes 80 joules. So then that means that number 2 is more efficient. Well, that would be incorrect to say because you're not looking at just the amount that's made. You're looking at what the input is as well. So, like for example, let's say that student number 1 produced, completed one piece of homework in 15 minutes. Student number 2 completed 2 pieces of homework in 5 hours. Well, even though student number 2 produced more, they're still less efficient because they needed more time to do that. They needed more input in order to accomplish that. So when it comes to efficiency, we're always talking about it in the form of a percentage, usually, or a ratio to compare. But first, let's move on to something that is higher tier, which is just methods of improving efficiency. So here are common examples of how we can have a lot of wasted energy. So for example, friction between moving parts causes heating. In wires, the resistance in a wire gets hot, which energy loss due to heat. Air resistance stopping causes a force on a moving object, so energy becomes dissipated as it's trying to overcome this force. When you have machines, you have sounds from machines that causes energy transfer to surroundings. So these are all examples of how energy can be wasted in a lot of common appliances or a lot of common settings. So you have to be able to identify how this can be reduced. So we already talked about how we can reduce friction, heat loss due to friction. We can lubricate stuff. For a resistance of a wire, though, resistance of a wire causes the wire to get hot when the current goes through. So let's think about what we can do then to reduce this. So there are some options. Is we can use we can have wires that have less resistance. Or we can shorten wires. So if it can't be helped, we have to use that piece of wire. Let's try to make it as short as possible, so there's less heat loss due to resistance in a wire. For air resistance, we can streamline shapes. To help it reduce the energy loss due to the air resistance. For sound, we can tighten loose parts to reduce vibrations. So for example, if you had a loose screw, you would hear it clanging about, which causes energy loss as sound. So if you tighten loose parts, reduce the sound that it creates, that would reduce the energy transfer to surroundings. Okay, so now on to the maths bit. This first equation that I've put here is basically just the law of conservation of energy written in equation form. Right? Input energy equals useful output plus wasted. Meaning, whatever you put in, the number that you put in has to equal the total number that you got out of it. So just like I did with my light bulbs, I have my input is electrical. 80 was my useful output, and then 20 was my wasted output. Both of these have to add up to whatever I put in. Because imagine if I had 80 joules of light and then let's say 60 joules of heat here, well that would break the law of conservation of energy. That wouldn't make any sense because I only put 100. Sorry, my microphone went off then. Because I only put 100 joules in the first place. So these two, whatever useful you have, whatever wasted you have to add up to whatever you put in. And so that leads into our equation for efficiency, which is basically going to be calculated as a percentage, which is just a ratio, of how much useful there is over the total. This is pretty much the same as I do when I calculate a mark that you got on a test. I put how much you scored over the total amount you could have scored. That's it. That's what efficiency is. So the equation itself is really simple. You have how much you have, the useful bit, over the total that you could have had, the total input energy. In order to get it as a percentage though, because when you do something divided by something else, you're going to get a decimal. To convert it to a percentage, you just times it by 100, and then you'll get it as a percent. So notice though that the top number can't ever really be bigger than the bottom number, because the bottom number, the total input energy, is how much you're putting in. So it's not possible to have more output than you had input. It's impossible to get more out than you put in the first place. Okay, so here's an example. A car engine is 25% efficient. How much input energy produces 100 joules of useful energy? So remember FIFA method, but the first things first is I gotta make a list of all of my information. A car engine is 25% efficient. So that's the first thing they told me. I'm underlining that and writing it in my list. 25%. I'm also gonna write it as a decimal. 25% as a decimal, because when you're changing it to a percentage, you're timesing by 100. To change it back to a decimal, you divide by 100. So 25 divided by 100 is 0.25. I'm going to write that in just because it's a lot easier to work with a decimal because our equation takes decimals. How much input energy produces 100 joules of useful energy? So how much input energy, I'm underlining that because that's also going in my list as a question mark, because that's what they're asking me to find. Produces 100 joules of useful energy. So useful energy equals 100 joules. Now the FIFA method. Formula. Efficiency equals useful output over total input. I insert values. So efficiency, I have a value for efficiency. Remember, I want to put the decimal in. So 0.25 is equal to useful output. I have a value for useful output, 100. Total input, I don't have. So I'm going to leave it as input by there. Okay, now to rearrange for input. Fine tune. Notice that input is at the bottom. Our variable is at the bottom. When you want to solve for a variable, when it's a denominator, you need to change it from being a denominator and bring it to the top level. So it can't be, you can't have it as a denominator. So I'm going to show you like the proper method, and then I'm going to show you what I want you to notice as the trick so you can do it quickly. So it might seem like a big old faff to do it this proper method, but then I'm going to show you the trick to do it quickly. Okay, so here is the maths theory behind it. To bring this to the top, I can times both sides by input. Like I was just rearranging. Input cancels out with input here. And I'm left with, let me just rub this off. And I'm left with input times 0.25 is equal to 100. Now I still want input, so I'm going to divide both sides by 0.25 now. That cancels out with that, and I'm left with 100 divided by 0.25. I'm going to write what we started with. This is what we had when we substituted everything in, so this was what we had when we substituted everything in. Notice that in order to rearrange for a variable that's at the bottom, all I did was did a little swapsy and swap this number around with that number. So notice how basically input went to where 0.25 was, and 0.25 went to where input was. So this is just a quick way to rearrange. You don't have to do all of these steps of doing the canceling out twice, because you basically, in order to solve for a variable that's at a denominator, you have to rearrange twice, which is a faff. So just the quick method is just for you to know, whenever you see a variable that you're trying to solve for at the bottom, it can just go swapsy with the whatever is on the other side of the equal sign, and then you put that on the bottom. So this, which is what we had when we first substituted in, so this is what we had when we first substituted in, became that. Okay, and then I just open my calculator. 100 divided by 0.25, that is 400 joules. So I had 400 joules of input energy. It's 25% efficient, so that means 100 joules was useful. How much was wasted then? So this is 400 joules input. 100 joules was useful. How much was wasted? $300. Very good. Because of the law of conservation of energy, if I inputted 400 and I got 100 useful out, then that means that the missing energy was wasted. So it was 300 that was wasted, because remember, the useful and the wasted have to add up to however much you put in. Now I'm going to help you with this one. Help you start off with this one, but feel free to work on it on your own if you'd like. A 45% efficient vehicle, so I'm underlining that, efficiency equals 45%. I want it as a decimal because that's what my equation takes, so that's 0.45. Transfers 1 kilojoules of energy as kinetic. This problem is tricky because it does not straight up say what's useful, what's wasted. Now think about it, this is a vehicle now. That 1 kilogram of energy that is kinetic, is that a wasted energy? Is that a useful energy? Is that an input energy? This is a vehicle now. What would I write here when I make my list? Am I going to write it as useful, wasted, or input? What is that? Think about how it's a vehicle. Very good. So, it's a vehicle, meaning it's a car. I want you to think about what energy goes into a car. Well, petrol, but petrol's chemical energy. And then it transfers, what's useful about a car is that it's going to transfer it into kinetic energy, which is the energy of movement. That's what we want from a car, right? We want it to move. But there's also going to be a lot of wasted energy in like the form of heat. Unless you're purposely putting the heater on in the car, we don't really like, the whole point is we want it to move. So, or sound even. So when it says 1 kilojoules of energy is kinetic, I know that's useful because it's a car, it's a vehicle, it's going to be useful. So I'm going to write useful is equal to 1 kilojoule, but remember we want all of this in regular joules. Kilo means 1,000, so that's 1,000 joules. How much chemical energy from the petrol did it use? Well, chemical energy was the input. So there we go. So the tricky thing about a problem like this is that there's layers to it. It did not, unlike the last problem, it did not explicitly say what is useful, what is wasted, what is the input. It just told you the actual energy stores. And so just like we did previous, where I gave you the example of the TV and the kettle, and then you guys wrote in the chat what energy was useful, what energy was wasted, you have to do the same thing here, but in the middle of a problem. So you had to decide for yourself, right, it just told me the energy stores. Now I'm going to work out which of these energy stores is what I want, which of these energy stores is what I started with, which of these energy stores was wasted. So now I have my list. Gonna write out my formula. Efficiency equals useful over input. Efficiency is 0.45, I'm substituting that in, is equal to useful, my list says 1,000, over input. Now remember, this is my variable, my input at the bottom. I can't rearrange unless it's on the top. Right now it's a denominator on the bottom. I wanted to bring it to the top. Easy way to do that is just do a little swapsy with that number there. So I can have input equals 1,000 over 0.45. And then I just stick that into the calculator. The reason why I showed you all of this earlier is to show you why the swapsy thing works. Because you're basically just doing the two rearranging steps in one, where you rearrange this, the input, over onto the left, and then you're rearranging the 0.45 to be on the right. You're doing it both at the same time, rather than needing to do all of the steps of the crossing out and everything. So 1,000 over 0.45 is crazy number 222. I'm gonna just round it to 2. So that should have been 2222 joules of chemical energy. Okay, so let's do a little bit of practice then. So let me link this again. Website by there. If you click on, actually let me just link directly to the Google Drive. That'll make it a bit easier. There we go. So there are some practice problems there. Remember, this is completely optional, so don't feel like you have to do this. I'll put the answers up to this in a second. But just to start you guys off with, there's some problems there where it gives you it in 3 different sections: practice, rearrange, and exam questions. So basically with the practice, you're not going to have to rearrange the efficiency equation at all. You just do the divide bit. But I want you guys to notice is the fact that you have to read through the questions and properly identify what is useful, what is input, what is wasted. So you have to make sure you're able to do that. Otherwise, you're going to get like the numbers swapped around if you misidentify a wasted energy as being useful. But remember, you guys are really good at identifying what's useful, what's wasted in the case of like the TV and the kettle. None of these examples are harder than that. It's just taking the time to really think about it rather than grabbing the first number that you see and holding on to it as, oh, this is going to be the useful one. So it's thinking it through, making the list, and then substituting it in, fine-tuning it if you need to, and then give your final answer. So I'll put the answers up in a moment, just so then you can check through your answers until you're happy with it. So we're nearly to the end of conservation and dissipation of energy now. We have one more lesson on it and then we're done before half term. For year 9s, you'll notice the topic that you're doing now, the next topic, is the conservation and dissipation of energy topic that Mr. Rugg has assigned. Just keep in mind, if you've been following along with my YouTube live stream, or you can go back and look at old videos, a lot of the stuff that we give, like the caboodle, all of that, that's optional. What you have to hand in is just the topic test, and then just do your educate. Those are the only 2 things that you actually need to hand in. The only time I would ask to see like what else you've been doing is if you completely bombed one of the topic tests where you did a lot worse than I know that you should be doing, because I've taught you, many times before. I've seen your test results. If you normally score like 90% and then you got like 10%, then I'd be like, okay, something's wrong here. They haven't bothered with doing anything. But my point is, in terms of what you have to worry about handing in, you just have to hand in the topic tests and the educate. That's it. That goes for year 10 as well. Just the topic test, just the educate. You don't need to hand anything else in unless you want it to go on Facebook, the distance learning gallery. So unless you want that, I'm happy to forward that on, but you don't have to hand anything else in unless I need to see evidence that you've done something. So when Mr. Rugg puts up like that huge list of work that you could do, that's suggested work to help you be able to do the topic test. So that's the point of it. So once again, this is optional. You don't have to hand in these problems to me. I'm going to put the answers up as well, so then you can check your work. The whole point of this is to help you feel confident and feel like you've got a grip on things, even though you're stuck at home. Being able to just feel confident with what you're doing. Okay? So answers are going to come up. If you're not sure about a particular answer later on, feel free to send me an email. My email is... Feel free to send me an email or leave a comment on Show My Homework or anything like that. Okay? Right. Have a good rest of the day, guys. I have a Zoom session with my tutor group now to check in on them and help them with their homework. So have a good rest of the day. Enjoy. Make sure that you're prioritizing your mental well-being. Mental health is always going to be number 1 in these kinds of situations. So have a good rest of the day, guys, and I'll put the answers up soon.